For homework, I prepared a module called homework, and in that I first define a new type called pay params, which just is a record type with two fields, recipient and loveless. Recipient is a payment pub key hash, loveless is just an integer. And I define a schema with one endpoint, which is called pay, and takes this just defined type as parameters. So the idea of the pay contract is to just make a simple payment to a pub key address of this amount of loveless that's specified here in the PP loveless field. So the contract doesn't make use of observable state, so I can use unit there. Then I use the schema I just defined, text error messages, and no interesting result type. So here in the first line, I block until the endpoint is called. So once the pay endpoint is called, recall the argument of this endpoint function is a function that takes as input the parameter type of the endpoint and returns a contract as output. So I'm using return here. Recall contract is a monad, so we always have return available. So what will return do? Well, it receives the parameter value of type pay params and then produces a contract that doesn't make use of any side effects that the contract could do. No blockchain stuff, no throwing of exceptions, no logging. It just immediately returns the value. So this is a contract that will immediately finish and return the passed in endpoint parameters. And then I use await promise to turn this promise into a contract. So this contract will block until the pay endpoint is called, and then the value of the contract will be the passed in parameters. So I bind them to PP, and now I construct a transaction. And I'm using this must pay to pub key constraint constructor that takes a recipient, which I take from the first field of the parameters, and it must contain a value. So PP loveless PP is just an integer, and there's a function loveless value of that will take this integer and convert it into a value of that amount of lovelesses. So this line says I want a transaction that has an output to a public key given by this address with this amount. Now the next line, submit transaction, will do two things. First, it takes these descriptions of what I want of my transaction, the constraints, and turns it into an actual transaction. So in particular, I want to pay this recipient a certain amount of loveless. In order to do that, the funds must come from somewhere, must come from my wallet. So what this submit transaction will do, it will try to balance the transaction by finding appropriate inputs in my wallet that are high enough to make this payment. And it will also, if the inputs don't fit exactly, which they normally won't do, create some change output that goes back to my wallet. And it will take the transaction fees into account. And once this transaction is constructed, it will submit it to the blockchain. And then in the last line, I recursively call the contract again so that it's still running and you can make another payment. Call the pay endpoint again. So the first thing I want you to do is write an emulator trace that exercises this contract. And the idea is it takes two integers as arguments, and then it should call the pay contract twice. So we must start the pay contract for wallet 1, and the recipient of the payments should in both cases be wallet 2. So you call the pay endpoint, wait one slot, call the pay endpoint again, wait another slot. So that's what this trace should do. So again, the recipient in both cases should be wallet 2, and the amount here, the PP loveless, should be given by the two parameters. So for the first payment, first argument, second payment, second argument. And then I define two functions that are called payTest1 and payTest2, both of type IO, that make use of this run emulator trace IO. So they call the trace you just defined with two different sets of parameters. So in the first case, you want to make a payment of 10 ADA and 20 ADA. In the second case, a payment of 1000 ADA and 20 ADA. I used another extension here that's called numeric underscores, and that allows me to, as the name suggests, put underscores into numeric literals. And especially when Loveless are involved, because one ADA is a million Loveless, these numbers get quite big, and it's sometimes not so easy to, at a glance, count the zeros. So this is nice in this case. To use this extension makes it a bit easier to read these large numbers. When we try this in the REPL, so first the pay test 1, then we see in the result there is indeed, this must be wallet 1 then. So this has lost roughly 30 ADA, and this wallet, which must be wallet 2, has gained 30 ADA. So the payments of 10 ADA and 20 ADA were successful. And if you want, you can check the trace here and check some more details. If, however, we try paytest 2, then we see that none of the values has changed. So no payment was successful. No transaction was actually successfully submitted. And if we think about it, it's clear why. Because I'm just running emulator traces with the default parameters by using run emulator trace IO, which in particular means that each wallet has the default initial funds, which is 100 ADA. So when the first payment is tried of 1000 ADA, that's too much. Wallet 1 doesn't have that much, it only has 100 ADA. So at this line here, line 32, as I explained, this submit transaction does two things: construct an actual transaction and then submit it. So during construction, that will fail because the balancing algorithm tries to find inputs in the wallet that will cover the payment, the 1000 ADA. But because there are only 100 ADA available, this will fail and it will throw an exception and will crash. So the pay contract will crash at that point. So in particular, the first payment doesn't happen, but neither does the second, because when the trace tries to call the pay endpoint a second time, the contract has already crashed. So none of the two payments will happen. So the second thing I want you to do is modify the pay contract by handling the exception. So somehow handle the exception so that if in this step here an exception happens, instead of throwing it, you just lock the error message. And that will have the effect that obviously you still can't make a payment of 1000 ADA if you only have 100, but the contract shouldn't crash at that point and the second payment should be successful. So after I've done that modification in my solution and try it again, then the paytest 1 should behave as before. And indeed we see the wallet again received the 30. But now the paytest 2, we see something has happened. So wallet 2 received 20 ADA, which was the second payment. So the first transaction with the 1000 ADA again failed, but the contract didn't crash because the exception was handled and the second payment succeeded. And if you look here in the trace, then we see here is the error message logged. So this is where I caught the error and I'm logging the error message, which in this case was insufficient funds, which is quite insightful. So it says it needed 1000 Loveless, but it only has 100 available. And this concludes this week's lecture, where you hopefully learned a bit about monads, how they work, why they are useful, and you saw two examples of monads that are particularly important for Plutus development, namely the emulator trace monad and the contract monad. So the emulator trace monad allows you to basically script scenarios that until now we have done by hand in the playground in the simulator tab. So it's a bit like scripting the simulator tab. And the contract monad allows you to write off-chain code. We have seen a couple of examples. We will see many more in the following lectures, but you can do similar things or all the things that you also could do by hand with the Cardano CLI. So you can query the blockchain and you can construct and submit transactions.